Hey there, it's Chris. Today we're talking about something that I've been thinking about for a while now, and something that I've been wanting to share my thoughts more on, but I just never got around to it. And so today's the day. And that topic is sort of exploring different architectures and trade-offs of implementing a state chart engine. And so it's a really nuanced topic in my opinion. I think there's lots of ways to go around it. Those ways aren't necessarily wrong, but there are boundaries and trade-offs, and um, I'm personally exploring this in a project that I've been working on with others called StateML. Um, so this is sort of our collective work and thought in this particular space. So to start off with, it's probably good to give an overview of what a state chart is, um, in order to understand how something can execute a state chart. So let's pan over here, and as you can see, state charts uh, um, are a visual notation for describing behavior and flows. And the first part of them is that they're an extension of finite state machines. So a finite state machine is a set of states and a set of transitions, and you can transition between states on a given event. Um, and what state charts do is they extend this formalism um, by adding by adding hierarchy, by adding structured or synchronous concurrency, and a whole bunch of other features. So I'm just going to go through very quickly what those features are, um, and then we could dive into more of the engine specifics. Um, in general, there are lots of variations of state charts out there, and so some might have other features, some might lack features. Um, the features of the notation I'm going over right now are specific to StateML. Um, so yeah, let's dive in. So to start off with, there's different types of states that can exist. The first is an atomic state, which is pretty much synonymous with what a finite state means in finite state machines. So this is like a qualitative state that you can name and be in and transition in and out of. The next type of state that there is a compound state. So this is where hierarchy is introduced. And essentially a compound state can contain um, any depth of states within it. So it can be atomic states, like I'm sort of visualized here. It could also be another compound state, right? And so there's this infinite nesting that can happen. Um, we'll talk about that a little more in the future. Um, there's also composite states. Historically, the composite states, as I'm calling them right now, have had different names. Originally, they were called orthogonal states. Over time, they might have been called uh, parallel states and like SCXML and XState. The reason that I'm calling composite states is because there's sort of a chemistry metaphor arising here of how we're putting states together, and I think it maps really well to the state chart formalism. So that's why we're using composite state. Now, what that is it's separate. It's a state made up of separate regions that are executing in a synchronously concurrent way. So when you enter this composite state, there's this region and this region, and they're able to react to events in a very concurrent manner. It's not necessarily parallel execution because it's synchronous concurrency. So there's some nuance there that we can get into. There's also some pseudo states. So these are states that have some extra functionality or some extra semantics or meaning to them. So a final state is when you enter a final state, you can't get out of it. You're done at that level of the hierarchy. You're done transitioning between states. And then there's history states, which is if you target a history state, it's going to remember the history of the state that it's in. And so it's also this like weird pseudo state that has this like extra functionality that's enhancing the state chart. So those are the core states that we can have. Um, uh, Default history. Cut that out. So yeah, these are the different. The next part of the notation is transition. So these like arrows between states, and here's a little overview of what those look like. So first off, there's some event that triggers the transition. That is always required. And then optionally, the transition can have a condition saying, hey, should we take this transition, right? And maybe that is looking at some extended state or something outside the state chart to determine that. There's also a target, so you can target a single state or potentially multiple states. That's also optional. And then at the end, there's some actions that we perform on this transition. So there's different types of triggers. I realized I'm missing one, so I'll just add it in now, which is the finish transition. So yeah, finish. So let's go through this. So first off, we have your typical event. This could be an external event being sent to the state chart from the outside world. And it could also be an internal event, which is what we call a raised event. So the trigger for that is on event E or on event E raised. So you can add an additional condition to say, we're expecting this to be just a raised event, right? And so again, this is these are all triggers, so you could essentially substitute it with this part of the transition. There's immediate transitions. We call them immediate. They have different names. So in SCXML, they're called eventless transitions. In XState, they're called always transitions. The reason that we're calling them immediate and they're using the keyword now is we're trying to make it time-based. But semantically, they're the same thing. So immediately when you enter a state, this transition is going to be activated. So it can be used to recreate choice states. That's another type of pseudostate that explicitly existed in the notation in the past. But once XCXML came around, this lower level primitive of immediate transitions was enabled, so we can create a pseudo choice state, but without explicitly calling it a choice state. And we can use these immediate transitions anywhere we want, which can be really powerful sometimes. Next up, we have delayed transitions. So these are transitions that are triggered after a certain period of time that a state is entered. So if we enter a state, after 1 second, this transition will happen. And that's really important for time-based behavior, which is a core part of the notation, in my opinion, and should have some kind of first-class way to be described without needing to deal with starting and canceling timers. So those are delayed transitions. We have the default history transition, which can only occur in a history state, and it's like the first time a history state is entered or is targeted, but there's no existing history in that state. We're going to use this default transition. And then there's the finish transition. Again, a time-based transition. It occurs in two different places, and it's synonymous with SCXML's done events. So there's two times it can happen. When a state enters a final state, the finish transition can be triggered. And in something we'll talk about in a second, when activity is spawned in and is bound to the lifetime of a state. When that activity finishes, that's another type of transition that we can take. So yeah. This brings us to the last and probably just as important part of the notation, which are the side effects that we can perform. Because state charts are a behavioral notation, the ability to act on our world, to interact with our world, so receive events and then act back, is really important. And we do that through side effects in a couple different ways. So the first type of side effect is called the first group of side effects are called actions. So these are there's sort of two types of actions that can exist, whether they're implicitly defined in a state chart engine or explicitly defined, depends on the implementation. But there's entry, exit, and transitions actions. So these are different times that we can call some side effect that does something. So entry is called when a state is entered, exit is called when a state is exited, and transitions actions happen when a transition is taken. Usually these are some form of callback that either perform a fire and forget side effect, which just means it doesn't really affect the internal state of the state chart. And then the other types of actions that happen might update some extended state of the state chart. They might raise an event or do something else. And those actions are affecting the future execution of the state chart. And then the other type of side effect that we have is what we're calling spawning an activity. In SCXML, this is typically called invoking a service. In XState, the newest version of XState, this is spawning an actor. We'll get into the nitty gritty of that in a little bit, but essentially we're calling back to the original name that Harel came up with in the state chart formalism called activity. And essentially what it is it's this entity whose lifetime is bound to the state that it is spawned in. So if we enter a state, we spawn activity A, and then we can communicate with that activity in a various number of ways. What's important in the notation is events that are sent up from that activity to the state chart. In StateML, we have a special channel. Each activity that is spawned has its own channel. That channel is sort of can only communicate with the activity that it is given to and from, and from a notation standpoint or a syntactic standpoint, you can say from activity A, if it sends me if this activity says it's finished, then we're going to do something. You could also say on event on E, do something, right? So that's an event sent from activity A. So that's that right there is sort of the notation of state charts, a really condensed version of state charts. There are definitely other features that exist in various implementations, but for StateML, we've sort of tried to make it as concise and expressive as possible. So now that we sort of know what a state chart is and what an engine, how an engine might interpret that notation, let's talk about some of the things that are important when trying to build a state chart engine from the ground up. And different projects might want to enable different things, but in general, these are the set of things that we're thinking about with the StateML project. Things that we want to make sure that the state chart engine can support without having to fork it, without having to do hacky things, or maybe there's just use cases that we couldn't have imagined that we're trying to enable, right? So we're trying to open up and make the state chart engine as extensible and as language agnostic and portable as possible. So first thing that you want a state chart engine to do is very bluntly to execute a state chart. So usually this is some textual description that is probably parsed into some machine representation, and then there are a set of semantics to execute that state chart. This recording in general is less concerned about semantics. The nitty gritty semantics, it's obviously an important topic. We're mainly following the object-oriented lineage of state charts that started with UML state charts and SXML. And yeah, there's semantics differences between that and sort of the original conception of state charts that came out of tools like StateMate. And so yeah, we're largely following that set of semantics with some deviation or variation. So yeah, that's obviously the most important thing that the state chart does. The next thing is we want the state chart engine to be as small as possible, and we also want to design it in a way that's portable. So both of these things are important. The smaller it is, the easier it is to port between languages, maybe compile it to WASM. And then when we think about portability, we're thinking about are we depending on features in a certain implementation that can't be found in other languages, right? That would not be portable. Or is there a way that we can, write this in some language that can compile to WASM and then be used in any language that supports WASM? So there are constraints and concerns that you want to think about if you're trying to make a state chart engine small and portable, so that it can be used across a varying set of programming languages. The next thing that is really important is inspection. To clarify, I'm talking about runtime inspection. So as a state chart is running, is there a way that we can get its current execution and visualize that, to interact with it, to see what's happening, to log it? That's a really important affordance of this particular notation, and we want to make sure that we're enabling that we're not trapping data and state inside the state chart, so that you can never see what's happening. And making sure that there's APIs in order to get that information out, right? And part of that inspection or introspection could enable using a state chart in some kind of JavaScript framework to render a UI, right? Like that's essentially how Xstate works, right? There's some kind of inspection API where you're sort of say, hey, the state chart is updated and now we need to re-render things, right? So there's an observability mechanism here that powers a lot of things, but also there's like a debugability and just like understanding the state and being able to visualize that is just as an important topic. The next thing that is really important is simulation. And so what I mean by that is, can we execute the state chart without a full implementation? This is really helpful if you're sort of in a modeling phase trying to figure things out, and maybe you want to click through the state chart and sort of simulate different paths in your head, right? It's a way for us to provide like a live programming experience without needing to fully implement the state chart. And so what's important here is, can we simulate step by step, and we'll get into a little more detail later on, like what that means. Can we simulate step by step the execution of the state chart and allow the user to provide any missing details as they're clicking through a specific use case or a specific path through the state chart? That is notoriously hard, and I don't think I've really seen many state chart engines be able to support that, like micro-step simulation. Another important thing that relates to being small and portable is the engine being unopinionated about extended state. In StateML, we've designed it in a way for this to happen. So it depends there are implementation details that further prevent a state chart engine from being very dependent on a certain type of extended state that it operates on. What we want to enable is there can be all kinds of extended state that you might want the state chart to operate on, and it should not restrict that. That's the main concern here. And yeah, that's important both across being portable across different languages, but also just enabling in a single language. Maybe you have you're just the extended state is a JavaScript object. Maybe in another use case, it's some JavaScript signals or an observable or the DOM itself, right? Like we shouldn't be unopinionated, or we shouldn't be opinionated about like what that extended state should be. And if we aren't, then it should open up a whole slew of use cases. And then the last thing, which definitely gets into the nitty gritty, but I think is such an interesting boundary to think about, is transition caching. And so there's two things that I mean here, and I'll elaborate on that in a little bit. But as you can tell, if we're caching something, it's usually related to performance, but it's also related to pre-compilation or build time compilation, right? Like, can we do certain types of computation up front, and then the state chart can be really fast? Or can we sort of swap out the runtime that's powering the core semantics of the state chart? So maybe we can detect, this is just a finite state machine, and just use a smaller and quicker set of semantics to execute that, as opposed to a full-blown state chart. And so maybe we could detect these things at compile time, and then swap out the associated runtime. Transition caching. I'm trying to look at as like a broader boundary that we can leverage in the future. So in my head, these are sort of the core things that we want to enable with the state chart engine. And yeah, let's dive into the details. So in general, to execute a state chart, we need two things. We need some machine representation of that state chart, some in-memory representation, and then we need an engine to execute that and to respond, to take events and then perform everything that it needs to do. In general, and this is more broadly speaking, the machine representation is not what you're authoring. Typically, there's some kind of textual representation that can be mapped back and forth between the machine representation. Sometimes they're the same, so maybe the user is authoring JSON, and you can, and a specific state chart engine is traversing and iterating through that JSON in order to execute the state chart, right? But in general, there's probably going to be a divergence in the representation that's important for the engine, and a divergence between like what someone would want to author with. So sometimes this could be a predefined grammar such as JSON, XML. Other times it can be an external DSL like StateML. And then the other way that, like, on the other end of the spectrum, there could be a visual representation for that someone's authoring in order to execute a state chart. And typically that's mapped between some machine representation and or textual representation. So there's these bidirectional arrows that go both ways. And in general, StateML has this is how StateML is architected, where there's a predefined grammar that I sort of walked through before, and then that is compiled to some machine representation that can be used by the engine, or by transformed into a visual representation that someone can both interact with and author. And if we have those things, then we have a state chart. We can execute a state chart. Now the engine, as you can see here, let me just move some of this stuff down. Might have some details that aren't specified in the representation of the state chart. Sometimes of what we call a schematic. So yeah, you can see that here. This is like partially pseudocode for like what the StateML engine, the API for the StateML engine looks like. So you essentially are defining a new class. You pass it the schematic, right, the machine representation that we've compiled from our textual language, and then you're also providing a set of implementations. In StateML, all implementations in the authoring format are named. So you're naming actions, you're naming conditions, you're naming activities. And you're providing those implementations later on, right? So part of the reason that's important, there's a couple reasons this boundary is important. Number one, it allows us to stay portable. We don't have to create like a least common denominator of this like implementation language across all these different programming languages. We could allow them to you to best leverage the parts of a particular programming language or programming environment that you want. Secondly, there's this like hole-driven development that one of our teammates, Bernard, was working on with his master's thesis or his senior thesis. About hole-driven development with state charts, which is pretty much maybe provide a name of an implementation, and that it sort of acts as a hole that we could fill in later. This also powers simulation, right? So we can mock out, right? Simulation is just the mocking of these holes and allowing a user to select what condition is true or something like that. And then thirdly, it allows us to it allows you to change those implementations. So the same state chart can have a different extended state and a different set of implementations associated with it. So yeah, I think this mental model of you describe the state chart and you're trying to think at a different level of abstraction, right? And names sort of are a buffer between that level of abstraction where you're trying to model the behavior of something, and then you how you want to fully implement it in a programming language. And so yeah, definitely keep that in your mind. But yeah, this is the high level surface area of the engine, and then you could select the engine and do a bunch of things with it, right? Send events to it, yada yada yada. So that brings us to what I would say are the three most important parts of an engine that exist in most engines in some various ways. So there's the event queue. This is part of the object-oriented state chart lineage, where we queue up events that are happening and we process them one at a time. So we'll talk about that in a second. Secondly, the second part is, let's say someone sends an event to the state machine. We need to figure out what transitions to select, right? And then once we know those transitions, we're essentially going to follow the arrow and trace out a set of instructions for the state chart to execute. And so let's like walk through an example of what that looks like. So we have a state chart right here. It's very contrived, but hopefully it gets the point across. Right now, the green states, these green borders represent the like active state that we're in, right? And so I'm going to walk through what happens with the state chart. So the first thing you might see is there's this built-in start event. So when you start a state chart, it needs to figure out what the initial states are. And because there's potentially infinitely nested hierarchy, it sort of recursively figures out what the initial states are, right? So you can see right here, P1 is the initial state of machine M. So we're going to enter state P1, and then you can see, let me just change this. Then you can see that state A is the initial state of P1, so we're also going to enter state A. So what you can see here is given some event, we're going to figure out what transitions to take, and then once we figure out what transitions to take, we sort of trace the, we sort of follow the arrows to derive a set of instructions for the state chart to execute. So the state chart's going to look at this and it's going to say, hey, I know that I'm going to do something when I see that we need to enter state P1. I'm going to do something when we need to enter state A, right? And so now we're in a valid starting state. And then you could see, let's say event E1 is sent to the state chart. What's going to happen is we're going to find the transitions that we need to take. So we're going to take this transition right here. So I'm just going to mark it blue. And then if we trace this transition, we're going to generate a set of instructions for the state chart to execute. So what you can see here is if we trace this line, we've crossed this border. So we're going to exit state A as defined right here. And then if we continue tracing, there's no actions or anything that we need to do until we hit the border of state B, in which case that means we enter state B, right? So given event E1, these are the set of actions we're going to do. Now let's say event E2 is sent to the state chart. What's going to happen? Well, first we need to figure out the transition. So there's no transition for event E2 in on B, because currently, if I update what our active states are, you can see that we're currently in event B. So there's no transition for event E2 in state B. So what we're going to do is we're going to traverse up the hierarchy, and we're going to say, okay, is there an event in P1? And there is. So we have a match. We have a match, and we know what transition we're going to take. So what we're going to do is we're going to follow the line and figure out what to do. So our line sort of starts in state B. We're exiting state B. And then what you're going to see is there's an exit action. We're also going to exit P1, but we need to perform the exit action before we actually exit state P1. So our first three instructions are to exit state B. So I'm gonna do that right now. Ready? We're gonna turn that black. We're gonna execute. Turn that black too. This is our active transition. We're gonna perform this exit action on state P1 called foo. So we're gonna call that. That gets called, and then we're gonna exit state P1. And then if you look at this transition, there's an action on it called bar. So we're gonna execute action bar. Now that is done, we're going to see that we hit a line here called, which is this state P2. So we're going to enter state P2. So let me make that green. And then state P2 has an entry action. So we're going to perform that, and that's called BAS. So we're going to execute that action. And then P2 is a compound state. So and its initial state is state C. So we're going to enter state C. Right. So this is the set of actions that the state chart is going to execute when we're sent E2. And so you could sort of like get a gist of like how I'm thinking about this. It's really just a set of transformations between the description or representation of the state chart and a set of actions that we want to execute. And hidden in there is how do we select events. So that's, in my head, what a state chart is doing when it's being executed. And so let's go back to these three things here, right? Technically, I guess what I didn't include is when an event is set, it is queued and then immediately executed. So just also keep that in mind. So let's start talking about event queuing. What are different implementations or ways to handle that? And what does it enable? So the best way, in my opinion, to talk about that is to understand what it an example of what it doesn't enable. So this is this is the SCXML spec that came out was started in 2005 and came out in reached 1.0 in 2015. And this is pseudocode describing the semantics of SCXML. So while you don't need to write an engine as exactly follows here, it is interesting to think about the implications of authoring a Statechart engine as the pseudocode lines out. So as you can see, the Statechart has a whole bunch of different things. The most important things at the moment are the internal queue and the external queue. So there's essentially two different queues that the Statechart has. And that manifests itself in the main event loop as nested while loops. So this outer nested while loop, is essentially continuing to loop until the Statechart is stopped or canceled or whatever, and it's processing external events off the event queue. One thing to notice here is that the queue is a blocking queue. So if there is no external event, this dequeue method is going to block until the Statechart gets an external event, which in general I would argue is not portable, is not the most portable across different programming languages. But what you can see is we process an event queue. We take a micro step based off our response to that event, and then we get stuck in this nested while loop, which executes the remaining micro steps. So what's important about Statechart execution is we might not just take a single transition given an external event. We could take any number of transitions giving an external event until the Statechart settles, right? And so that step of transition, that sequence of transitions is usually called a macro step or a big step, and each individual transition is sometimes called a micro step or a small step. They're all used synonymously. And so this while loop defines the unknown number of micro steps that we might take until there's no more to do. So the first thing we do is we look for eventless transitions, which is what I'm calling immediate transitions, and we execute those. And then what we do is we look at the internal event queue, which could be events that are raised, and then we say, oh, maybe there's a raised event, we need to process that. So what's important here is there's nested while loops, and each type of transition or event that we might be processing is handled differently. It's in a separate queue, or it might not even be queued up in the case of immediate transitions. And one of the things that this makes really hard is microstep simulation, because we have synchronously running while loops that are nested. So we can't just break out of a while loop and then resume, because we'd have to resume back into the nested loop in certain cases. And so it makes it really hard to pause the synchronous execution that's happening here, right? And so that stems from two things. One, the first insight here, and this is an idea that my teammate Bernard came up with, was if we normalize, there's two things. The first is there's all these different events happening that have a different priority, right? So immediate transitions have a higher priority than raised events, which have a higher priority than external events. And that is represented in this double queue, nested while loop kind of fashion, but it doesn't have to be. And second, not all events are normalized into a queue, including the start and stop event, which isn't shown here, but it's partly shown here, right? You can see that we enter the states based on the initial transition of the document, and that triggers a whole cascade of things. But what's important here is there's these implicit events that are defined in this particular implementation, and they're not normalized as events. So what we came up with, and that has worked quite good, is our Statechart engine has a single priority queue. So everything that the engine does is queued up on this priority queue, and all these different types of built-in events, start, stop, immediate transitions, raised events, external events, all of them have a different priority. And so they're just synchronously executed until the queue is empty. Normalizing everything as an event makes it really easy to break out of this single while loop and resume the single while loop, which means we could arbitrarily pause the execution of the state chart as it's processing events. And this enables microsteps simulation quite trivially. All that you need to do is provide the stubbed or mocked implementations for the state chart. And on every microstep, you pause the execution. So those are the two things you need to do to enable microstep simulation if we use a single priority queue. The other thing this enables is, and we haven't explored this too much yet, but this enables some really cool queue visualization while you're doing simulation or even runtime execution. We could easily serialize the queue into an array and simulate it in some kind of inspector or simulator. And yeah, it's really easy to, because everything's just in a single event queue. So that's sort of the first boundary that's really interesting, and as you can see, it sort of checks off this one, right? So that brings us to something that I'll comment on, which is runtime inspection. Runtime inspection has more to do with the execution of or the surface area of the engine rather than like particular implementation details, and it's pretty much just conceptually it's just emitting some kind of an event that says, hey, the machine just settled, a microstep just happened, an event just got sent to us that we ignored. If we emit all of those things via some kind of inspection API, we can easily achieve this. And I guess the other thing with a priority queue, there's different ways you can implement a priority queue, but I think the easiest one for what we're doing, which is we're always queuing off the highest priority event, but we can append to arbitrary sections of the queue, is a linked list. And in general, that's going to be a lot more accessible to. I think that's going to be a lot more portable across different programming languages than the blocking queue, internal queue thing that SCXML sort of recommends. It's also a step towards portability as well. Let's go into the next two things, which are sort of related, and they're the core things that the state chart does. So we're either queuing an event or processing that event, and if we're processing an event, we need to figure out what transitions to select and what instructions do we generate and execute. In general, transition selection shows up in two ways. The first way is are more like optimizations, which are pretty straightforward. So if you're trying to select a set of transitions, as I sort of walk through in this example, there's this like hierarchical kind of algorithm that you need to follow, which is pretty much you start at an atomic state and you say, is there a transition here? Then you say, no, okay, let me go up to its parent state. Is there a transition here, right? And it's recursive. And then when you have when you have a composite state where there's like multiple things synchronously running, you need to do that for both regions. So it's sort of a really expensive operation to do. And one of the ways to optimize that, and I would just like to point out that Jacob, this is something I picked up from Jacob Beard's master's thesis on Statechart engines and optimizing Statechart engines in his project called Scion, is to collapse transitions into a single array at an atomic state. What I mean by that is instead of navigating the hierarchy every time every time we need to like try to figure out what transitions to select, we can store and sort of collapse this hierarchy into a single array for each atomic state. So how that would work is you can see like state A right here, right? It has transition E, and it also sort of like behaviorally inherits transition E2. And if we in the instantiation of the Statechart engine just collapse this onto state A, we can just traverse through a list of transitions instead of traversing through the entire Statechart hierarchy, which should be much quicker to do. So this is more like of an optimization and data structure that we can do to accompany that. And then the other thing that there's prior art on is we can sort of cache. We can cache the transitions that we just determined given the set of current active states and the event that was passed in. So all you would need to do to cache, in my head, is to take the current state configuration, the current set of active states, and the event, and turn it into a unique ID or string. And if that's your key, then you could just get the events from that. And if it would have to be just in time because of the way composite states work, where there's like there's sort of state explosion that happens. There's a state explosion that happens because composite states represent the orthogonal product of all the states in each region. So it makes it really hard to cache this ahead of time because there can be potentially a lot of configurations that we just don't even know could be. But it doesn't mean it's impossible to. We could be selective about this. But conceptually, yeah, there is probably going to be some just-in-time caching of these transitions, so that if it happens again, we could really quickly select that transition. So that's sort of the two parts of transition selection. The next part is, okay, we know what transitions that we want to take, and now we need the state chart to figure out what to actually do with it. And so conceptually, that is sort of just tracing the transition and getting the low-level instructions in order to figure that out that we walked through before. Now, there's some really interesting things along this section. So if we have some kind of transition cache or instruction cache, there's a couple things that we might want to do that we need to think of. So we might want to pre-compile this instruction cache. What's important here is we can cache the instructions for a single transition, right? Or also known as a microstep. What we can't do is we can't cache a certain set of transitions, because in the worst case, it can be infinitely long, or it could be infinitely or it could just be changing because you can have conditions on any transition. So the only static piece of information that we know in the description of the state chart is a single transition. And what we can do is we could easily look at that transition and cache this array of instructions. And then all the state chart engine is doing is it's just looping through this set of instructions and doing something with it. So there's a couple different ways that we can do this type of caching. It could be just in time. So we can say, hey, we haven't seen this transition before. Let's figure out what instructions that we need to execute for it, and cache that for future reference. We can also pre-compute these ahead of time when the state chart is instantiated, or during compile time, and just potentially pass in that cache, right? And so that brings up the important boundary here. If our instruction generation logic is externalized and can be passed in as an implementation, there's a whole slew of things that that enables that the state chart doesn't care about. So maybe by default, the engine caches instructions just in time. But if you want to compile ahead of time, you could just pass that to the state chart. If you want to compile everything upon creation, you could pass that to the state chart, for example. And if that logic to generate instructions is sort of coupled to the cache, essentially what we've done is we've externalized the selection logic from we've externalized the selection logic from any particular type of state chart implementation. So this is also what could enable swapping out the underlying runtime, right? Is if we swap out the transition selection logic and the instruction generation logic, you could potentially swap out any runtime. And more importantly, let's say you want to add a new type of pseudostate or a new type of transition, you can extend the existing runtime to do that, and you can update the set of instructions that we need to execute by the state chart. So there's a really interesting extensibility aspect about this is if we find the right boundaries for transition caching, it's going to enable a lot more things than just good performance. So that's sort of the core part of the state chart that we've been exploring, and I think there's some really promising stuff so far. Now it's almost been an hour, so I'm gonna try to wrap this up soon. But I did post on Twitter that I was gonna record this video, and just was trying to gauge if anyone had any particular questions. I got a couple different questions. So the first one was by David Khorshid, who works on Stately and on XState. And his question was about the semantics of action execution, particularly if an action or a condition or any implementation throws an error, what are the semantics for how the engine should catch that, right? So first, I'm going to remind you, these implementations are filling in holes for the schematic. So the the assumption here is that, like, if you just forget about implementations for a sec, the engine should never throw an error if it's implemented correctly, right? And so that what that means is that, assuming the schematic that is passed is correct, right? So there is a contract there, but if the schematic is correct, the engine should be able to operate on it without any errors. Number two, what that means is that the errors that can originate in a state chart can only happen from these holes that we're filling in at runtime. And that leaves a really interesting question, which is, let's say an error happens in an action or a condition. I think the answer to this question is, can we continue executing and just ignore that error, right? We can't really provide much recovery. I feel like recovery is increasingly hard the deeper you get into this particular topic, right? So let's look at this little example we have here. So let's say foo throws, right? Action foo throws. Can we continue executing the state chart? That is the big question. If foo, if you remember in the beginning of this video, I talked about there's two different types of actions. There's these fire and forget actions that update some part of the world that we probably don't care about. And then there's actions that update the state that the state chart depends on, right? The extended state, maybe it raises an event. So if we can tell that there's a difference between these things, maybe if it's a fire and forget action, then we can continue executing as normal and just not care about the error. If it's an internal action, right, we're updating the extended state, raising an event, if we know that that's the action being executed, then I would argue that the state chart can't continue because it's future. A really important part of this notation is determinism, right? We want, given the same order of events, we want the same things to happen. And part of that is in the user's control, part of that is ingrained into the notation. And so from a semantic perspective, I feel like we can't continue executing in the latter case at all. And so I think if an error happens in this particular type of hole, the state chart engine just needs to stop. And it's on the user to catch those errors from happening, or some type of type system, right? So that's my thought there. My thought on the former case, right? So you have some kind of fire and forget action, which is maybe you can stop, but you can just ignore errors in that case. But I think in general, there could be other, like, how do we know that there isn't, like, someone could be updating anything and we could in some roundabout way be affecting the determinism of the state chart. So let's say there's a fire and forget action that's updating some DOM node and that errors out. Now an event that we thought was going to be emitted isn't emitted. Is that affecting the determinism of the state chart? It's a fire and forget action that's operating on the outside world and isn't directly impacting the execution of the state chart. But I worry that there's a lot of cases where there's like this really like this spookiness at a distance kind of thing that is like would actually affect the determinism of the state chart execution. And I would almost lean towards we should also rely on the user to catch errors happening there too. For conditions, I think the answer is pretty obvious. If a condition, which means we have a transition and we're deciding whether to take it or not, and the event matches, and we're just saying, hey, if some part of the event payload matches this thing, then we should take this transition. And that throws an error, then we just can't. That affects the direct determinism of the state chart, and I don't think we can continue execution there. So we'd also have to just abort execution and let the user know that an error was thrown. It would be on the user to catch those errors and then tell us what to do based on that for that condition. And then same thing with activities too. I think the same logic applies. So I think I would universally say if an implementation throws an error, then we need to. It's on the user to catch those errors and report them and figure out what to do with them. The state chart can't figure that out because it doesn't have the context to, and it would ultimately, if there was some form of recovery, it would ultimately affect. I don't know how we can make it deterministic. So that's sort of my answer to David's question. We've got the type safety in a little bit. Related, the semantics of updating extended state. I'll get into this. This is a question by I think Christian, and they were sort of just asking about portability and like how do you update extended state. I could answer that in the context of StateML. So I'm not trying to say there's a right answer, but for StateML, we're trying to be very opinionated about extended state. So we're sort of leaving this up to the user. By default, I would, in most programming languages, the extended state is going to be just mutable, and actions are just methods or closures that just mutably update some extended state. And there's always one copy of the extended state, and then you don't have to worry about, well, this transition is seeing this extended state, and this other transition seeing this different extended state, and that doesn't make sense. There's a whole like can of worms that opens up once you start having a more immutable data model for your extended state. And I've sort of seen this happen with XState too, and I'm not sure. It was definitely a big problem in XState v4, and I know there was some flags introduced to try to work around that. And those flags came at probably a big memory and performance cost, because you sort of had to save all these existing snapshots and then pretend they existed. That's sort of a different story though. So in general, we're trying to be very unopinionated about this, and it's really up to what you. It's sort of like something that you and someone authoring the state chart is in control of. I think that's sort of where we've landed on extended state. I had another thought. I don't remember. So yeah, that's sort of what I would say around that. And because of that unopinionatedness, it's ideally going to be portable across different programming languages, because the state chart engine doesn't really care. And the other thing to take in context here is the engine that we're creating is definitely lower level than what I would consider something like XState. And so what that means is that there's definitely ways that someone can extend our engine, build something more meaningful on top of it, maybe some kind of immutable extended state on top of it if they want to be more opinionated about that. But the engine we're writing is again trying to be as small and portable as possible. So that means we're trying to open up different extensibility points in order to enable that. The next question was by Parker Codes, which was sort of about communication between different entities in the state chart. Barker was specifically talking about XState and actors. And I think what I want to say there is that I want to be very clear that the activities as defined in StateML are not actors. They may look actor-like because there is some form of event communication, but the actor model has very strict boundaries about what an actor is, right? So there's strong encapsulation of memory, there's asynchronous event communication, and asynchronous message queuing. And sometimes that's really useful, particularly in the context that Parker was talking about with like maybe you have a state chart in Rust and it's communicating with a state chart in JavaScript because I think they work on Tari, which does something like that. So in that case, like maybe an actor-like communication in a state chart makes sense. But there's also other times when you don't want that, particularly if you're writing a like you're sort of nesting some state charts in a user interface and it's on a single thread, and maybe you just want to like use a more object-oriented synchronous method dispatching kind of thing. In access, you want weak encapsulation and you want synchronous event passing or something like that. So for the engine, and as I've outlined, like the engine that we're writing is trying to be as extensible and portable as possible. So I think supporting both cases is going to be really important here. And what it comes down to is we don't we have a very small and extendable interface for how to enable this, right? And so it's what I'm calling our activity interface, which is an activity can do four things. It could send an event up to the state chart that created it. An activity is told when it should be stopped. An activity can say it's finished, and it could return a reference to itself, right? And with those four things, we could potentially support any number of patterns and styles, whether it's actor-like or whether it's not, right? And the most important thing is we're returning the activity has this channel to communicate with the state chart, and then it also returns a reference, which could literally be anything. And this is something that we infer at the type level, and you can just access. And you can take that reference, you could send an event to it. Maybe you can access some state on that. Maybe you call a method synchronously. There's all different types of things that you can do. And so we're trying to like open up that particular point and making it as extensible as possible to support all types of use cases. And then the last thing, the question by Mert, which was about type safety. I'll demo this in a sec, but in terms of type safety, because StateML is typically used as an external language, there's a compilation step, and depending on the build tooling and the type system we're talking about, we can have really good type safety. So I'm particularly talking about when you're using StateML in JavaScript or TypeScript, well, specifically in TypeScript with some kind of build tool. We could have really good type safety, and I'll show you how that works. We've also had some promising prototypes that Bernard's been working on in C# via the Roslyn generator. Languages that don't have a build system that can handle external DSLs, we could have some kind of CLI that maybe generates types or generates things that would be useful for that language, and that's a little more unknown because it's very dependent on the language and its build build tools. So let's get into the demo. Essentially what I have here is a little StateML schematic that is some kind of import form, and there's an active state and a state when the form is disabled. And if the form is active, then we could have different focus states and different types of validation, and the validation is asynchronous, right? In which case we're spawning some kind of activity that validates whether the form is valid or not. So yeah, this is our form, and this is what it's going to look like in JavaScript. So we're going to have a form, and it's going to be a new engine. Oops. And let me just import. Right. So we're gonna have our engine. Next, what we're going to do, we're going to import our we're going to import our schematic from the HTML file. So, oops. Form input, and we already what happens is this is a Vite project. So there's a Vite plugin for StateML that says if the file's a StateML, compile it to StateML, and then also output a declaration file to generate types for it. And we'll talk about that in a sec. So what you see right now is we have an input form. Our type gen is already created. I'll just save this to refresh it. And then what you see here is there's going to be a bunch of arrows because we haven't provided the correct implementations or implemented the holes correctly. So you can see right here, right, our actions, we have an action called set value. So let's implement that right now. Set value. Oops. So we're going to define some actions, and you could see it's going to autocomplete. Now it's still going to throw errors because there's other implementations. So you know, just in my head, I know that there's going to be some kind of validating activity, and we will talk about that in a second. So I'm just going to throw in a little empty just an empty function here, and it's going to return a reference. Let's just make it 1 right now, or true. Now the last thing that we need to do is we need to implement some conditions. So the condition is disabled, and it obviously autocompletes. So let's implement that. Right now, our form has some kind of value associated with it. So let's just add a little variable here. So we're going to have a variable called form, and we're going to do value equals form dot external event dot dot value. Right? Maybe we have some kind of I guess this could be undefined, but yeah, maybe we have some kind of some kind of value here. And then maybe we disable the form when value.length equals 0. Right. So now we have our now we've implemented our things, right? So let me show you how each of these works. So actions are given a specific channel to tell the state chart to emit a certain events or to erase certain events, right? So they're given some methods to do that. Activities are given a special channel, so they could be finished and they could send events back to the state chart. Those are the two things that an activity can do, and then they could return a reference. So what's cool is we could easily create utility functions that abstract away this logic. So let's say we want to spawn a promise. We could just bring in the spawn promise helper, and maybe we just promise that resolve true for example. Or I think how the logic works here is, if the promise resolves, then it's valid. If it rejects, there's an error thrown. But you could implement that. You resolve a Boolean instead, and then if an error is thrown, you handle that a different way. There's different ways, right? So we could have a little utility function that just very simply abstracts over that implementation, and you can see what that looks like right here. This is all it's doing, is just instantiating that promise lazily, and then when the promise finishes, we send resolve up, and then we call finished, and we also return the data that was passed to it, and then we catch any errors, and if so, we send a rejected up. I guess in this case, we could also omit the finished event as well, or maybe this would be a better way. Really, maybe finally we call finished, and we get rid of it here. So that's sort of how you can implement declarative wrappers upon this. Now here's what's interesting. If you take the state chart, we can check what states it's in, and we can easily derive all the possible states that you can be in via this helper. We can also infer the activities that we might have instantiated. So we could do form.get activity. This is auto-completed because the only activity that we've defined is called validating. And if we look, it's a promise that doesn't return anything, or it's undefined, right? Because depending on what state we're in, we might have spawned this or not. But you can see we inferred that we're spawning a promise. So you can get complete type safety for any activity that you're implementing and then referencing directly. And that's going to be really important, because there might be times when you're directly referencing, grabbing a reference to an activity and doing something with it. And so the ability to type that and infer those typings is really important. How does this work? So it gets into a topic that we'll talk about next time. But essentially what we're doing is we're just creating we're taking the machine representation, right? So there's a compiler in StateML, and it outputs what we call a table / a graph. That table is JSON serializable, which means we can also just make it a TypeScript type. So all we're doing is we're bringing the output of the compiler, the machine representation that the engine operates on, and we're defining that as a TypeScript type, and we're attaching that to the export of the StateML file that you're importing, right? So if we look at this, that type, form input type gen, is literally just the representation that the compiler is outputting, which is pretty cool. I'll get into what this representation is next time. All you need to know is that it's an array of the entire state chart, and we can do some. We could have some very simple utility types here. So these are all the utility types for type gen that can extract all different types of things. So if we want to extract all the state charts, we can just take that type, and there's a little pattern matching utility type that just gets all the states from the state chart, and then grabs their state path and creates a union out of them. Same thing for any events that the state chart emits, any external events, any raised events. any action names, activity names. So we can grab all these things from this representation. We can even do cool things like get all the events emitted from an activity, which is pretty cool. And in the future, we can probably do things like figure out in TypeScript like events uh, what events does this action see, right? We can do things like that as well, which is pretty cool. So that's sort of how TypeScript, that's how type safety and type gen works in StateML. It's, again, this is a prototype, so it's bound to change. Maybe things won't work out, maybe things will. Everything that I've seen so far seems pretty promising along this along this avenue. And yeah, that's sort of what I talked about today. So thanks for listening. Till next time.